Hello everyone and welcome to my talk, Reinforcement Learning in Physics-Inspired Semi-Markov Environment. New materials are critical to the advancement of science and society. A really nice example of a material that most people know is carbon fiber. Carbon fiber has made bicycles, sailboats, and even hockey sticks stronger and lighter than they were with their legacy materials. Materials design process, however, is quite burdensome. It's iterative, time-consuming, expensive, and human-dependent. And this opens the door, at least slightly, to the idea of AI-aided human design. In this work, we investigate the suitability of deep reinforcement learning for materials science. We focus on a specific challenge within the realm of materials science, that is semi-Markov decision processes. To understand and analyze this, we have developed a physics-inspired RL environment for deep reinforcement learning. As this is an initial study, we evaluate the performance of deep RL methods within this environment. I'll first begin with some background. Markov decision processes, or MDPs, are a formalization of sequential decision-making problems. In MDPs, the agent interacts with the environment and takes actions that influence the reward and next state emitted from the environment. In an MDP, the state emitted from the environment is considered fully observable. As a result, the agent can know everything it needs to know in order to choose its next action based on its current state. In partially observable MDPs, or POMDPs, on the other hand, the state information emitted from the environment is not sufficient for an RL agent to optimally select its next action. In this work, we focus on environments that are a blend of fully and partially observable states. We refer to this as Semi-Markov problems. Semi-Markov problems are particularly interesting within materials design application. Reinforcement learning agents interact with the environment in a sequence of discrete time steps at a given time. With a given state, the agent picks an action to take next. As a result of taking the action, it receives the reward at the next time step along with the next state. The RL agent aims to learn a policy via online and simulated experience that maps states and actions to a probability distribution which maximizes the discounted sum of rewards. The environment that we have developed simulates the state changes incurred by a material when it is operated on by heat and work. The environment is shown pictographically on the right. I will discuss the details of this in the next slides. The objective of the agent in this environment is to apply heat and work in order to transition the material from the start state to some goal state. The challenge is elevated by the fact that there is a nonlinear relationship between heat, work, temperature, and pressure. In the phase change environment, there are 3 material phases. These are colored yellow, blue, and orange in the graphic. Within each phase, the state transition dynamics are fully observable. The phase change boundaries divide each phase. The boundaries are shown as gray. Within the phase change boundaries, the dynamics are partially observable. We have one fixed goal in the environment. The goal is marked by the red rectangle at the top. When the agent reaches the goal, it receives a reward of 1 and the episode ends. At all other time steps, the agent receives a reward of 0. This mix of 0 reward on time steps other than arriving at the goal implies that the problem has a sparse reward. we evaluate the RL agent from 3 different start locations. The difficulty of the problem is a function of both the distance from the goal and the number of phase change boundaries that the agent has to cross in order to arrive at the goal. Therefore, the dark green start location in the rectangle at the bottom is the hardest start point, as it has to cross 1 or 2 phase change boundaries depending on the route it chooses, and has a large distance to travel. As I mentioned before, the agent has 4 actions available to it. The actions are adding and removing a fixed increment of heat and work. The most interesting aspect of the environment is that the state transition dynamics are a mix of fully and partially observable. Within each phase, the agent picks an action and moves in an unknown but deterministic direction and distance from its current location. For example, if the agent is at the point marked by the red circle in the yellow phase, and the agent takes action 1, it moves 1 step down along the pressure axis. Once the agent has entered the partially observable phase change boundary, it takes 2 time steps and a sequence of 2 actions in order to leave the boundary. If an agent at time t is at the start point marked by the red circle, for example, and wants to move to the point inside the orange phase marked by the black circle, it must first take the action 3. From the agent's perspective at time t plus 1, it will still be in the same state. This is the partially observable component of the problem. At time t plus 1, the agent must then take action 1. This will result in the agent transitioning into the point marked by the black circle in the orange phase. At time t plus 2, the environment will then return the new location marked by the black circle. In our experiments, we use deep Q learning. This is an off-policy value-based RL method. It's one of the sort of baseline methods used in modern deep reinforcement learning. The network, which is schematically shown on the right, takes the state as the input, which is represented in terms of temperature and pressure. The output of the network is the value of each possible action given the current state. The agent selects the next action to take according to an epsilon greedy policy. The agent is trained with batches of 128 tuples of experience. In addition to DQN, we evaluate deep recurrent Q learning. DRQN is expected to be more robust to the partially observable phase change boundaries due to its internal memory. In these experiments, we use GRU for the recurrent layer. As before, the agent employs an epsilon greedy policy and is trained on batches of 128 tuples of experience. In order to improve performance due to the sparsity in rewards, we test both DQN and DRQN with hindsight experience replay. This technique combats sparsity by reimagining a small portion of the failed actions as successes. Through our experiments, we aim to answer the following questions. What is the impact of partial observability in the phase change boundary on DQN agents? And is the memory in DRQN sufficient to solve this simple Semi-Markov problem? The plot on the top left shows the results of the DQN agent starting from the 3 locations, the easy location, moderate location, and the hard location. It is clear from this plot that the DQN agent starting from the hardest position is significantly worse than the DQN agent starting from the easier positions. This is shown by the gap between the yellow line and the blue and pink lines. We also see that the agent starting from the hard location has a much higher variance than the other two starting locations. I will now focus primarily on agents starting from the hard location, as these are the most interesting results. But if you want to see more details, please refer to the paper. To understand the impact of the semi-Markov phase change boundaries, we rerun these experiments without the partially observable phase change boundaries. The fully observable results appear in the plot on the right. This comparison shows that the partially observability in the phase change boundaries has much more of an impact on learning than the distance of the start to the goal. This is seen by the smaller gap and the lower variance in the yellow line on the right, in comparison to the semi-Markov plot on the left. In comparison with DRQN, which is shown in the lower plot, DQN is significantly worse. In this plot, DRQN appears capable to handle the semi-Markov problem quite well. In 10,000 episodes of training, DQN learns a policy that takes over 2,000 steps to reach the goal, whereas DRQN takes just over 500. With closer inspection, however, the comparison between DRQN on the Markov and semi-Markov setups shows that DRQN is not fully optimal on the semi-Markov problem. If DRQN were to completely solve the semi-Markov problem, it would learn a policy that takes around 40 steps to the goal, as it does in the Markov setup. This result shows the benefit of incorporating hindsight experience replay into training both DQN and DRQN. We see that hindsight experience replay does not help the agents to solve the partially observable phase change boundaries, but it does improve the efficiency at which the agents learn policies to apply within the phases. This is shown by the number of steps for DQN, which is reduced to 195, highlighted in red, and the number of steps for DRQN, which is reduced to 145, highlighted in blue. Our final result shows the state visit distribution for DRQN trained with hindsight experience replay after increasing episodes of training. The visit frequency averaged over the first 10 episodes of training shows that the agent spends a lot of time stuck in the phase change boundaries and at the edges of the state space. This is depicted by the darker purple cells. After approximately 200 episodes of training, we see that the agent is traveling relatively directly from the start position, marked by the blue circle, to the goal position, marked by the red circle. Although it is better than it was in the earlier phase of life, the agent is still struggling with the phase change boundary. This is shown by the purple cells overlapping with the gray phase change boundaries. Finally, after 400 episodes of training, it is still inhibited by the phase change boundaries. Indeed, no matter how much training we do, this inhibition never goes away. This emphasizes the fact that the memory in the DRQN is not sufficient to fully handle the partially observable boundaries in this environment. To summarize, in this work, we have undertaken an analysis of the capabilities of standard deep reinforcement learning methods for semi-Markov sequential decision-making problems based on our developed material phase change environment. Our results show that DRQN leads to better performance than DQN, and that both methods benefit from training with hindsight experience replay. However, the GRU memory in DRQN is not sufficient to completely handle the partially observable phase change boundaries. Whilst the RL methods considered have not fully solved the partially observable problem, DRQN has shown promise. Our ongoing work is looking at alternative methods for deep RL and means of handling partial observability, such as incorporating LSTMs. In general, we want to promote materials science and scientific lab research as an intriguing testbed for RL, with many interesting challenges. This includes partial observability, which we have studied in this work, but also observation costs, sensor variability, and the potential for RL agents to interact with multiple weak dynamics models. Thank you very much for your attention, and I look forward to taking your questions online.